Okay. Hi, everybody. Thanks for listening in. Today, I'm going to talk a little bit about the night sky and how things appear to move across it. This is going to address very basic observational questions in astronomy, like why does the sun appear to rise and set? Why are certain constellations visible to us here in Idaho at particular times of year? Why are certain stars or other astronomical objects just not visible to particular observers? But also kind of fundamental things like why does summer and winter happen? Why do seasons work the way they do? Why is it cold in the winter and warmer during summer? And even things you might not think about so much as why does the moon, how fast does the moon spin? And why are the phases of the moon what they are? And for dramatic events like, say, eclipses, why do those happen so rarely at particular locations? These are all tied to kind of a fundamental theme, which is tied to our perspective, or more technically, reference frames. Most of you have heard the statement, the reason the sun rises and sets is because the earth is a spinning ball. And hopefully you've all heard this statement and will repeat it perfectly fine. The trick is, what are the implications of that? And understanding that this isn't just a statement, it can provide you with insight into other aspects of astronomy. For example, it's true that the sun rises and sets each day, and that is due to Earth's rotation. But because the fact the sun rises and sets each day is not due to something specific about the sun, it's due to how the Earth itself moves, that actually has implications. It's not just the sun that rises and sets each day. The moon rises and sets each day. All the stars you see in the night sky rise and set each day. And you can see that most clearly when you see long exposure images, which allow stars to be formed into streaks. These all rise on one side of the horizon and set on the western side, except for stars right around the north, directly north of us, around something called the North Celestial Pole. All of this property arises naturally if this motion isn't due to all of the different astronomical objects, but just because we are on a spinning ball of rock that basically makes it so that we can only see half the sky at a time. The reason the sun appears to rise and set is because as the Earth spins, the sun will first be invisible, but then appear and move from right to, and then appear as the Earth moves, and this thing, and basically Idaho comes close to directly under the sun. Then the sun is very high in the sky. Then as it continues to move, the sun gets lower in the sky and sets. This basic behavior can make sense. But transitioning between being a person on Earth and taking this outside perspective is honestly a little bit challenging. And I want to push on it a bit because there are a variety of consequences of this perspective shift that need to be kept in mind and can help you to understand things like, why does the moon have different phases at different times? Why is it that certain constellations are really hard to see in the winter or the summer? Those sorts of things require us to take a closer look at this perspective shift. So let's do that. And we'll do it first by focusing on the stars, because their motion in our sky is simplest. Because we're not moving that much relative to the stars. So if we imagine the Earth as a spinning ball here, around the Earth's position, each star is more or less in one position. It varies a little bit as Earth moves, but not by very much. There are certain stars that are directly over Earth's North Pole. There are other stars that are in other directions. Now, each of those stars is its own distance away, but as far as we're concerned of what direction they are, we can project that direction onto a single sphere known as the celestial sphere. Celestial just means sky. So if we basically ask where the direction to each star pokes through that sphere, we have basically projected all of the stars onto a single spherical shell. Now, is that actually where the stars are? No, but it does accurately encode the directions to each star. We're just suppressing the information about distance, which is harder to measure. Okay, and the nice thing about having everything on this spherical shell is it's a two-dimensional surface. It's like the surface of the Earth. And like the surface of the Earth, you can turn it into a map. This is, in fact, a sky map. You can find these all over the place. Now, since you're taking a sphere and turning it into a rectangular map, this distorts things, just like it distorts the surface of the Earth. If it becomes particularly distorted near the poles of that sphere. And conventionally, these maps often work like Earth maps. This is a map where the North Pole is at the top, but the pole has been turned into an edge. The South Pole has similarly been done to that. And this makes Antarctica and Greenland highly distorted. The same thing is happening here. Distances between stars are getting distorted. At the upper edge, which is near the North Pole, the region in the sky that is directly above Earth's North Pole, and the South Celestial Pole, which is the region directly south of Earth's South Pole. And we have various things in between. And you can locate any star or any astronomical object somewhere on this thing. Here is the constellation of Orion, which most people have seen. Here is Cassiopeia, which is far to the north. The Big Dipper is partially cut off, but basically up here. And this big blue bar is the Milky Way galaxy projected on our sky in this particular description. So that's one nice thing about the idea of a celestial sphere. It provides you a way to show you where all the stars are in textbooks or astronomical almanacs, which is great. The other thing about it is it lets us start to understand how to go from our perspective of a person here on Earth to a perspective of where are these stars relative to us? What is visible? The idea here is this. It's the real world has the Earth spinning on an axis, and all of the stars are more or less fixed in place. But we can kind of get what stars we can see by flipping that picture around. We imagine the Earth is fixed. Is it really fixed? No, but this is our perspective as someone sitting at a particular spot on Earth, which basically is Idaho in this picture. If we now flip that, we go from the Earth spinning and the stars being fixed to the Earth being fixed and this celestial sphere rotating about this axis. It rotates in the opposite direction, of course. And this starts revealing why the stars look the way they do in those long pictures. We see little circles because basically each of these stars is moving on a little circle about this axis. So the ones near the North Pole or even the South Pole, if you're there, look like circles. But whereas stars on greater distances at basically different latitudes move on larger spheres or larger circles. The trick comes when you recognize that we are on the ground, we are on Earth, we are on an opaque surface. We can't see this entire sphere from any given location. We can only see things where Earth doesn't block it. This creates what's called the horizon, which can be represented by this blue circle here. This is basically the location where we can see things above that, but we can't see anything below it because it's blocked by the Earth. In fact, versions of this graphic often show the horizon as a flat plane because it's just there to indicate the parts we can't ever see. But it is there, we just can't see it. And the important thing to understand is this divides stars into three very basic groups. There are stars that are always above the horizon, no matter how this thing, no matter what the orientation state of the celestial sphere or the Earth is, they're always above the horizon. These are ones around the North Celestial Pole. There are stars we can never see because they are below the horizon at all times. No matter how Earth spins or how the celestial sphere spins, whichever one you like, they are never above the horizon. They are invisible to us. And there are stars that are sometimes above the horizon. And the thing is, which stars are which are naturally represented in this map. Again, this is a sky map where the North Celestial Pole is at the top, the South Celestial Pole is at the bottom. Stars near the North Celestial Pole are always above the horizon, and so are always visible every night, assuming it's not cloudy or smoky. Similarly, there's a collection of stars near the South Celestial Pole that never get above the horizon. Us here in Idaho don't get to see them. If you want to see them, you need to get further south on Earth. Go to a place like you could go to Florida, Hawaii, or go all the way to Australia and New Zealand, or even Antarctica. The thing is, there are objects here that we just honestly never get to see. One example of that is not just stars, it's this thing. This is a galaxy. It's called the Large Magellanic Cloud. It is a galaxy that is currently colliding with the Milky Way. If you want to study this, you can't do it from Idaho. It's just never above the horizon. We don't get to see this. This is a picture of the night sky from New Zealand. They get to see this all the time. Their sky has and telescopes here have access to study those objects that we just don't have this far north. But these guys never get to see Polaris and rarely get to see Cassiopeia or Big Dipper. So that's one reason why astronomers like to put telescopes all over the place, because otherwise we wouldn't be able to study these things. But there's more to it than that. There is this entire collection of stars that do get above the horizon, but there's certain times when we can't see most of them. And the reason for that is because there are not just stars in the sky, there is also the sun, which is a star, but because it's so close, it's exceptionally bright. What that means is even if those stars are above our horizon for some amount of time, it's really hard to see them because basically they're up during the day. So if the sun is here and we're here, these objects, these stars are hard to see because they're just up during the day when it's hard to look at stars. For what that means, now, turns out, for example, the sun is roughly here right now in the celestial sphere. And it turns out it's fairly close to Orion. So turns out in the summer, we're in late summer now, Orion is hard to see because it is fairly close to the sun. It's not impossible at, just after the sun sets, you might, or the sun rises, depending on which season we're in, it might be possible to see Orion. But those opportunities are limited. The thing is, which stars the sun is near changes over time, because over the course of a year, the Earth moves around the sun. And so which stars are basically behind the sun changes. And the sun, in fact, over the course of a year, moves through the sky following a path called the ecliptic. And so during summer, so in the summer it's here, around equinox it's here, now winter it's here, equinox it's here. And it just follows this path once every year. In fact, of course, the Earth is going around the sun, which is causing its apparent position to change, but it's still a useful picture. What it means is in the winter, the Orion constellation is now really far from the sun. So it's easy to see during the night. And this is why Orion is classically a winter constellation. It's easiest to see during that time. So that's one thing to understand. These stars that are sometimes above the horizon and sometimes not, which ones we can see depends on what time of year it is. And this has all sorts of implications because you can't move your telescope on Earth to get around this. All of the telescopes on Earth are going to be dealing with the fact that Orion is near the sun at some point. So if something happens in Orion and the sun is near it, nobody on Earth is going to see it. Now, so that's one aspect of this sort of motion that you can start to get your head around. Another bit that's really important for life here on Earth is the path the sun takes through the sky. It's not a flat line in this plot. It goes up and down. The sun moves north and south in the sky. Why is that? Well, that's because the Earth's spin axis is tilted relative to its orbit plane. This is something called an obliquity. It turns out that if something is spinning around a particular axis in space, no matter how it moves, that axis tends to stay fixed. Okay. What does that mean? Well, it means at some times, the spin axis is tilted, well, let's be more specific. The North Pole is tilted towards the sun. This happens in summer. Other times, the North Pole is tilted away from the sun. This happens in northern winter. I should be clear about this. This tilting towards is northern summer. This is northern winter. And that is not a coincidence. That is very critically because of this tilt. Why is this tilt important? Well, if the sun is closer to the North Pole, it gets moved to a point that's higher in the sky and spends more time above the horizon. If it shifts to the south, it is lower in the sky and spends less time above the horizon. You guys have all experienced this, and you're going to experience it here quite dramatically. Over the course of the next few months, the amount of time the sun is above the horizon is going to get shorter and shorter as we head towards winter. That means we get less solar heating. It makes it colder. The other thing is, as the sun moves, as the sun gets what's called lower in the sky, when we're on the half of the hemisphere that's tilted away from the sun, the amount of light gets spread over a larger area, which reduces solar heating further. These two effects together, the length of day and the basically higher angle of the sun, basically causes the atmosphere to cool when we're in winter, when the pole is tilted away from the sun, and be warmer when our northern pole is tilted towards the sun. This is why summer is the hot season and the winter is the cooler, if not actually cold as much nowadays, season. And the reverse is true in the southern hemisphere. The southern hemisphere in June is the pole is tilted away. The southern hemisphere receives less light. It is in winter. In December, when the South Pole is tilted this way, it is in summer. So we can also start to see that this path of the sun through the sky gives us information about seasons and how they work on it. And the thing is, this fundamental thing about the Earth's spin axis being tilted from its orbit motion is common. Many planets have this property. Saturn does, for example. Many planets have seasonal phenomena that are driven by the same basic physics. It's just the fact that the spin axis is tilted basically leads to different amounts of light hitting the northern and southern hemispheres over the course of the year. Now, the last object I want to talk about a bit is the moon, which is the other object you see moving through the sky a lot. And the moon is notable mostly because it exhibits phases. You can sometimes see a full moon, you can sometimes see a crescent moon, and this is its own thing, because what we're seeing here is now the effect not only of how the moon moves relative to the Earth, but also how the moon moves relative to the sun, because unlike the sun, the moon does not emit its own light. It's all light reflected off its surface that comes originally from the sun. And this is why the moon has phases. Now, the standard picture is this one. We have sunlight coming in from one direction. And we have Earth here, half lit, half dark. Here's the moon. The moon is also half lit, half dark. But which half we see here on Earth depends on where the moon is in its orbit. The moon goes around in a circle. When the moon is over here between the Earth and the sun, we're looking at the dark side. So we see new moon or maybe crescent moons, depending on exactly where you are. If the moon is here or here, you see a half moon, first quarter, last quarter, but half. If the moon is here, you see the lit side of the moon. So you see a full moon. And the moon goes around once every month, which is about 29 and a half days. So it goes through this cycle every month. Now, the thing about this is that this basic fact, which I think most people get some sense of, has immediate implications for where and when you can see these phases. For example, say that you're told that somebody sees the moon in the middle of the night. What phase are they seeing? Well, if they're seeing the moon in the middle of the night, they're standing here because Earth, in the middle of the night, you're here. If the moon is high in the sky, it's probably close to full. If the moon is high in the sky, it can't possibly be a crescent moon, because if it was a crescent moon, it would be over here, which just isn't visible if you're in the middle of the night. If you're looking The only time you can see a crescent moon is usually if you're near the boundary between light and dark, which is dawn and dusk. Things like that are important to keep in mind because they reflect very basic aspects of how this sort of illumination works. Although it's really easy to make mistakes, and it's one of the reasons science pedants can sometimes go, that can't possibly be a crescent moon because it's the wrong time of day. But it also is there to allow you to figure this out, that it's not just a memorization thing, that crescent moons aren't visible during the middle of the night. If you can think about this picture, you can figure that out. Now, the other aspect of this I want to mention at this point is the fact that the moon has a light side and a dark side leads people to talk about things like the dark side of the moon, that there's a side of the moon the sun does not shine on, which is not true. That would only be true if the moon wasn't rotating at all. And the moon is in fact rotating. It's rotating though in a very curious way. This is a graphic showing you what the moon could look like. It's just a bunch of pictures as it rotates through. And what you will see is you see the same features in the moon all the time. There's a bunch of dark patches and a bunch of light patches, which we'll get into. The darkness and lightness move across the moon as the phase changes, but the side of the moon we're seeing is constant. It changes a little bit, but we're always seeing the same side of the moon. The moon does not have a well-defined lit side and dark side. Right now, this part is lit, now it's dark, now it's going to be lit again. So there's no distinct lit and dark side. Well, there is, but it's not permanent. But there is a side of the moon that faces us and a side of the moon that faces away from us. This says that the moon rotates in a very peculiar way. Well, it's not that peculiar, but in a very specific way. The side of the moon facing the Earth is always the same, which I'll indicate here with orange. The side of the moon not facing the Earth is indicated here in blue. As we go around, we see that the side that's facing Earth changes. It's pointing to the right here and to the left here. That tells, so the moon is rotating, but it rotates at the same rate it moves. So the rotation period of the moon is 1 month, which is also its orbit period. Now, that is not a coincidence. Many moons do this. This turns out to be a consequence of the gravitational interactions between the Earth and the moon, which we'll talk about in a bit more in a later session. So, the final thing I want to talk about are eclipses. Eclipses are phenomenal events. I hope you all got to see the one that happened a few years ago that actually crossed through Idaho. There's another one, if you didn't, there's another one coming up in a few years. What these are times where we exploit the fact that the moon and the sun are the same approximate size. Either the moon blocks the light from the sun, or the Earth blocks the light from the moon. During a solar eclipse, which are the more dramatic ones, the moon passes between the sun and the Earth and blocks some of the light at some locations on Earth. For a lunar eclipse, the moon passes through the shadow of the Earth. So the Earth blocks the light from the sun, and so the moon goes through the shadow. And so the moon goes dark. Now, the thing about this, if you think about it a bit, this ties eclipses directly to lunar phases. In this case, the sun is coming from left to right, but if we go back to this picture where it's coming in from the right side, the only time that the moon can block sunlight from getting to the Earth is when it's right here. You can only get a solar eclipse during a new moon. Similarly, the only time that the moon can pass through the shadow of the Earth is when it's over here. So you can only get a lunar eclipse during a full moon. And this one's usually the more important one, because it's like when I was a kid, I went like, well, wait, what's the difference between a new moon and a lunar eclipse? A lunar eclipse is a full moon which suddenly becomes dark and then bright again due to passing through Earth's shadow, whereas a new moon is just the dark side of the moon. Now, and this just is one, and again, a thing you could just memorize, but if you start thinking about these different perspectives, it starts to just make sense kind of intuitively with a little bit of practice. Now, the last thing, though, I want to highlight is a limitation of these kind of drawings. This kind of drawing suggests that every time there's a new moon, the moon is here, there should be a solar eclipse. And every time the moon is on this side and there's a full moon, there should be a lunar eclipse. That's not the case. If that were the case, we would have solar eclipses every month, and they wouldn't be as special as they are. What's happening here? Well, the thing to understand is that this picture is two-dimensional. It's because it's drawn that way. The real world is three-dimensional. And that third dimension is important because if the moon is a little bit above the Earth's sun line or below it, it can't block the light, and so you don't get an eclipse. And this is in fact really important. The moon's orbit is actually tilted slightly from the Earth's orbit. And so for most of the year, the moon passes above or below where it needs to be to either give us a solar eclipse or experience a lunar eclipse. And just like the orientation of the Earth is fixed, the orientation of this tilt is fixed. So at one point in the year, the moon is high when it passes on the sunward side of the Earth. Then half a year later, it's low. There's only 2 times each year that the moon is basically not above or below, it's right on the line, and when you will get a solar and lunar eclipse. So there's only basically 2 times during the year that this can happen. Furthermore, okay, we should get solar and lunar eclipses twice a year. And that's actually about right, but it's not quite the full story. The thing is, the shadow of the moon is actually fairly tightly confined. The moon is a lot smaller than the Earth is. So the region that the moon blocks from the sun is actually fairly small. It can be represented like this, which defines a very narrow track. In fact, we now have actual pictures of eclipses from astronauts on various space stations, and it looks like a dark block. It looks like a shadow, which is what it is. What this means is, for solar eclipses at least, these only appear in specific locations. So if you're not at the right place, you're not going to see it. This is where all of the next few eclipses are going to be. And there's one that's going to come through the United States in 2024. There's this one, which is not quite a full eclipse, that'll cross southern Idaho in 2023. This is the one that's going to happen later this year. It's happening in 2021 in December, and wouldn't it be great to see? I'm not paying for you all to go to Antarctica. Anyway, but this is a bunch to take in, but I'm hoping you're getting a sense here of how having different perspectives on astronomical systems can help you make sense of what at first seems to be a bunch of disparate factoids. Thank you for your attention, and I'll see you next time.